All right. So in my last lecture that I did earlier, an hour ago, I think it only took us about 35 minutes to get through this, and there wasn't enough time afterwards to really start a new problem. But that's actually it's going to be pretty okay for us. It's like a slow introduction to this. If you look at the syllabus, what we're going to be doing is what we're covering today. This will be more like part one of ice tables, and we'll talk about what ice tables mean very shortly. And then what we'll do is we can do more examples on Monday, and then we even have Wednesday for chapter 15. So it's a pretty nice buffer where we're building up. So let's go slow instead of fast, especially, since I'm not physically present in the classroom with you guys. So the way I want to start off is to cover basically the two major ideas, even though the last lecture I gave you, after the quiz was about 30 minutes long. What we're going to do on this slide is like the key take-home part of that first part of the chapter. So let's start with this then. So the first question I have is asking me to write the equilibrium constant expression. So expression means I'm not going to have numbers in there. It's only going to be symbols or variables. Sometimes you might see this written as the mass action equation. I addressed that in the last video. It's just because literally mass is moving around. And it's asking us to solve for the balanced chemical equation here. So what I'll do is just to get everyone's mind back into, thinking about chapter 15. So when we're talking about the equilibrium constant K, if we're dealing with concentrations, we'll use the subscript C. We've seen other ones where we use the subscript P. There's many more than that. You can also keep it generic as just K, and it's implied in what the units are. That's fine. But effectively what it comes down to, right, it's going to be products raised to some power over reactants raised to some power, right? The way I even just keep it as simple in my head is just products over reactants. And for a while it gets confusing, especially under pressure. A lot of my students will write reactants over products because they read from left to right. But take stock before attacking. All right. So what I'm going to do is I'm going to hand this over to you guys for about 30 seconds or so. And so since it's one thing to wait in class and I can read your faces, but I'm going to have to set a timer so I don't sit here awkwardly in silence. I'm going to give you guys 30 seconds, and I have the participant window open, so I'm going to just randomly call on people. I hate cold call. If you don't know, it's fine. Just let me know. So I want you to write the K expression, the equilibrium constant expression for the reaction we have there. So give yourself 30 seconds. Even if you can only get the denominator or just the numerator, go for that. All right, so it's been 30 seconds. So let's just start with this. Bianca, do you want to jump on this? Just either give me the numerator, denominator, whatever you want, or the whole thing if you got it.
Wouldn't the products be the 0.198 tabulum?
Sorry. So maybe I should have done is black this up. So everything I'm just looking when I'm asking for the expression, all I'm looking for are the variables. So the only thing that should be popping up in this expression are these. That's all. No, you're good.
2H top.
So say again. Oh, you broke up a little.
Sorry, the 2HI on the top.
Yep. And so how do you want me to write that though? Just like this or different?
It'll be HI to the second.
It would be, right? Because we want to make sure we have the concentration of whatever our products are raised to an exponent, right? And that exponent, I know I made it such a big deal when we were talking about rate laws. And when you're writing a rate law, you can't take from the balanced chemical reaction. When you are dealing with equilibrium or any system in equilibrium, instead of just dealing with initial rates, once it's hit equilibrium, you can use the balanced chemical equation, the coefficients. So for us, yes, I can just reach into the balanced chemical reaction and pull out the exponent. So I 100% agree. Bianca, do you want to finish off the denominator or you want to pass it on?
I was just going to say maybe it's H plus I to the second. because they both are 2.
It looks like that, and actually, it's funny. It's like an epiphany because I finally realized why a lot of my students will write this. They'll say the concentration of H2 plus the concentration of I2, and it's actually the very first thing that my 10 a.m. section did. So even though we have a plus here, the way, and if you need a reminder, go back to the video that I put on YouTube. Because we derive this expression from multiplication, it's actually the reactants will be multiplied by each other. So that's the concentration of H2 multiplied by the concentration of I2 on the denominator. It's not written explicitly, but let me change the color here, right? Theoretically, there's a 1 in front of the H. Sorry about that. There's a 1 in front of the H and there's a 1 in front of the I2. It's just implied. The same thing about the exponents. They're just implied to be 1 if you don't write anything. Are we good with that? All right, so I mentioned this in my last class. I know I keep doing that. It's called a leading question. It's what I'm used to doing in lecture. I realize asking if we're okay with that usually doesn't work online. So it's almost like force of habit. So usually I would read your faces and I can't see them. So I'm going to work over the weekend. Is there a better system of asking you guys questions instead of being like, is this good? And keeping it open-ended. So give me some time to adjust. But again, if you have a question, talk over me. That is totally fine. My last class was doing that a lot. And that's what I want you guys to do if you have questions. All right. So actually what we have written here, even though it kind of looks a little bit messy with the highlighters and stuff, but that's the answer. That is my equilibrium expression. It boils down to products over reactants. That's it. If you're still a little iffy on it, don't worry. We're going to do a boatload on this because it goes into chapter 16 as well. So this at the top was just writing the expression. Now on the bottom, I'm going to want you to give me a numerical value for K. So that's going to be the difference if I ask you for expression, just means variables, and then numerical value means a number, right? So let me rewrite again, and Bianca, what you gave me. There's my products over my reactants raised to their appropriate exponents. And now it's asking me to find the value. So if I read what it's asking me, what is the numerical value of the equilibrium constant? So that's what I'm solving for. And if I read through the problem, it says the equilibrium concentrations. So remember, these are the concentrations of H2, I2, and HI that in their proportions will be at equilibrium. And that means those concentrations will stay that way literally until the universe ends, unless you act on that system. And then it gives us some numbers. The 0.0262 molar, that's going to be the concentration of H2. There's the concentration of I2 and the concentration of HI. I don't know if people have seen that phrasing before, respectively. If you ever see that in literature, what that means is the first number that shows up is the first variable. The second number is the second variable. The third number is the third variable. That's what respectively means. All right, that's a lot of talking. Now we actually find out it's really easy to calculate the equilibrium constant. It's just plug and chug at this point. So my expression is the concentration of HI, specifically at equilibrium, squared. Well, there's my concentration. Squared. And so I'll take a 2-second pause just to make a point here. So I didn't write down molarity next to the number, and there's a reason for that. This goes beyond this course why, but equilibrium constants typically are expressed without units. So don't worry about trying to cancel out your molars like you would if you were solving for the rate constant little k. The reason for it, I'll leave it at this, is it's actually derived from something called activities, and activities are a ratio, and so ratios are unitless, and then it gets kind of applied to these equilibrium constants, so that will be unitless for us. So in a weird way, it makes your life a little easier. So there's my equilibrium concentration of my products squared, and then I can plug in the equilibrium concentrations of H2, as well as I2. So give yourself 10 seconds, just so we're actually, active participation type stuff. I'll give you 15 seconds. Throw those into a calculator. and see if we get a number. Well, not if. Tell me what number you get. How about that? So Hannah, I don't know if you had a calculator with you. Were you able to get a number?
Yeah, I got 0.748.
Let me double check mine. Maybe I screwed up the numbers. So I didn't. Did I get that number? No, I didn't. Did someone else get a different number? So I could have screwed up though. That's what I'm saying. But I usually when this happens, I'll try to get two other people to confirm.
No, I probably did.
No, you're good. You're good. I'm just saying, like, this is how I usually do so. So yep,
7.1.
7.1.
57.1.
Yeah, so that's what I got was 57.1. So, Hannah, what I just recommend is maybe just double checking the math, go a little bit slower. The way that I went through it was like I would do, because this is more complicated, do the multiplication in the denominator first, save it, do the square on the numerator, save it, and then divide the two numbers. And that should get around the problem. But I agree, it should be 57.1. So at least this one works. My earlier class, I'd messed up the 6 and the 2s. They all got switched, and we had weird numbers, but we're in good shape.
Yeah, I fixed it.
All right, great. Awesome. So we're all on board with that. So those two questions, those representative questions, that is like the gist, the heart of what the first part of Chapter 15 is. So let's move on a little bit. So the next part, the major part of this lecture is going to be, how do I use that number for the equilibrium constant? And so we're only going to do this problem. It does take a good bit of time to get through, so probably the rest of the lecture. I would like to have more like feedback back and forth, but this is going to be the first time that we do a problem like this. And then for just the sake of flow and for, not to waste your time, I'm going to slowly go through this one, not asking for help from you guys. If you notice I mess something up, or if you have a question, or even if if you need me to clarify something, just, yell at me. I'll immediately stop and then, clarify it. So no problem with just interrupting. The only thing is, once I start writing with a stylus, I just noticed in my last class that I can't see the chat anymore. So if you are typing in chat, I won't be able to see that until I switch out from the stylus tool. All right. So with that said, why don't we get started? So we have this problem. Let's read through it, and then what we'll do is I'm going to switch to Microsoft Word, and I'm going to do everything out by hand. So I would recommend writing this problem down really quick too, so you can refer back to it. So it says at a certain temperature, 700 K, a half a mole of HI, I don't know why that I is bolded, don't worry. HI is added to 2-liter container and allowed to come to equilibrium. It's asking us to calculate the equilibrium concentrations of H2, I2, and HI, and it also gives us the equilibrium constant. And so I guess there must probably a small rounding error is what it was. That's why I had you do that last problem, because I just stole the numbers from this one. So it should be 57. And then we have our balanced chemical reaction. So what I'm going to do, because for the sake of space, is I'm going to move to Word, like I said, and then I'm going to write down our givens and finds, and then we'll start attacking the problem. So I'm going to stop sharing this. Oops. It moved everything. There we go. And then what I'll start sharing is just a blank Microsoft Word document. So that's what you should be able to see right now. And yell at me if you're not able to, you can't see it. All right. So let's write down some givens and some finds. Oops, keep getting weird tools. There we go. So my givens. On all the problems, I will give you a temperature. We've seen this before. There's certain information that I do need to give you to make a problem technically true. Sometimes you don't need to use every variable. Something like temperature. Why? Another definition for equilibrium constant we saw was K forward over K reverse, right? Talking about the equilibrium constants. And then because of the Arrhenius equation, right? We know that K is related to temperature. And so we see here, if K is, well, I don't know why that did that. If K and T are related, and K and big K are related, well, that means equilibrium constants are affected by temperature. So by me giving you this number, it's a requisite to make the problem technically correct, though we'll actually never use the number 700. So that's kind of hopefully a clarifying point on that. We were given the number of moles of HI gas, and we said we had a half a mole. That half a mole of gas was charged into a 2-liter container. And then some information we were given is that the equilibrium constant, the numerical value, is 57.0. And like we said, not having units is exactly what we want for K. Just before we even start, and I've made a decision now, this is from previous slides that I've had, where I've had give you a little bit extra work to get you guys thinking. I know it's hard being, doing this remotely. So I'm not going to do this in the future. What I've done is effectively given you concentration, but I broke it apart, right? Our definition of molarity is moles per liter. So even though I told you the number of moles of gas and the volume that the gas is in, that's effectively giving you concentration. Because what I see here is I have a half a mole in a 2-liter volume. If I do that concentration out, actually let me do it this way. If I do that math out, the concentration of HI ends up being 0.250 molar. So in the future, like I said, I will simplify things where I'm not going to give you that extra step. Let's just see if we can, my main goal is let's get to the heart of things rather than let's try to, do everything. So let me erase what I have here. Let's set up a quick sketch, and you don't have to do this every time. This is just to get my point across of what's happening. I have some sort of 2-liter container. That's what it told me. And it says I have a half a mole of HI gas in there. So it's just floating around happy, right? In real life, as soon as you start charging, what charging means to add gas to something. So once you've charged, start charging this container, actually the equilibrium process immediately starts. But we're going to take a hypothetical approach because it actually works out just fine. It's almost like having a state function. We'll pretend like we can magically put in exactly 0.5 moles of HI into a 2-liter container and then pause time. So that will be our initial amount. So we're not letting any sort of reactions happen. So that would be our initial amount. We'll unpause time, and so we're going to let things change. That means maybe reactants go to products, maybe some products go to reactants, but some sort of change is going to happen. And then, given enough time, an equilibrium is going to be established after that reaction happens. So what we see here is going to be our acronym ICE. So if you see on the syllabus it said we're doing ICE tables today, it's going to stand for initial, change, and equilibrium. So let's see how to apply this, at least this roadmap that we have, the ICE roadmap. Let me just remind myself real quick what I need to find, and then we'll get started. Ultimately, what I'm trying to get to is going to be the concentration of H2 gas, specifically at equilibrium, I2 gas at equilibrium, and then HI at equilibrium. Right? I usually use those subscripts, though the book usually doesn't, because if I took these two pieces of information like I just did a little while ago, and then calculated out the concentration of HI, we said that was equal to 0.250 molar. That was the initial concentration. So using subscripts are going to be helpful in organizing your math for this. So that's our givens and finds. So I'm already recording the video, so if it's going a little too quickly, you can always come back later. So keep that in mind as you're doing these problems too. So just for the sake of time though, I'm going to keep moving on. But like I said, if I hit something where it's just like, I just don't get what's going on, immediately stop me. So let's take a pause. I'm going to write this really big on purpose. There's our balanced chemical reaction. I've left out states of matter. They're all gases. It's just for clarity. If we set up our roadmap of initial, change, and equilibrium, right? We can ask what is happening at each stage, right? We said at the initial stage, I charge the container and then I pause time. The change stage, I will let either the forward or the reverse reaction happen, whatever, is dictated by the equilibrium constant. And we'll talk more about that later. And then eventually we'll hit a new concentration that is going to be at equilibrium. And so that's kind of our roadmap. So initially, we need to take a look from our givens table to figure out what am I starting with, right? Well, initially, I know I was starting with a 1/4 molar of HI. And so I've had students in the past ask, why did I convert it into molarity first when I was just given moles? It's because by definition, the Kc that is given to us is designed to only work with concentrations. It cannot deal with amounts. Amounts are like numbers, like the number of things. It doesn't work. It needs to be in concentration. If we're using Kp, and I'll do examples of this on Monday maybe. If not, I'll try to put some practice problems in. Right? Kp just means it has to be in pressure. So it is dictated what units you use by that subscript next to the K. So I'm in molarity, so I'm good shape. There was no additional information in the problem telling me anything about the concentrations that I started with of H2 and I2. A very reasonable assumption, and because it's the way the problem is explained, is I started with nothing, right? The only thing it said I did was charge that container with some HI gas. That's it. So I've set up my initial concentrations. It's 0 for both what was traditionally called reactants, and then 1/4 molar for what we traditionally call products. We'll get into this more when we talk about Le Chatelier's principle, but now because we have forward and reverse reaction, this is not like, I wouldn't say like the most, well, I'll even put it this way, but everyone says that. I've even actually seen it in papers, so I would take it as, yes, this is what we call it. To distinguish, because, here we can actually see, we're going to predict the reaction is going to go in reverse. And if you can't see that, we'll see why in a second. I'll walk us through it. But the reaction is going to go in reverse. And so it gets a little confusing talking about reactants and products. So a lot of the time, what you'll see is we'll refer to the left and the right of the reaction. And the left is our traditional reactants, and the right is our traditional products. But if it gets confusing, and I'll usually use left and right in the future, it helps you figure out, am I talking about going this way or am I going that way? But again, we'll see more of this when we get to Le Chatelier's principle. So again, small steps. I don't want to overwhelm you guys. All right, so we have our initial concentration. I unpause time and I let the reaction happen. So I could theoretically think, even though it's not going to happen, I can ask the question, could a reaction happen in the forward direction? The answer is no, absolutely not. There's nothing here to react. There's no way for the forward reaction to go forward, right? You cannot create something out of nothing, so the reaction cannot go forward. There is an equilibrium. That is just by the arrows tell us that, and the problem told us that. So that what this is going to tell us then is we're going to be consuming, which will represent as a negative sign, my traditional products. So it's going to be consuming the right-hand side of the reaction, and it will be forming compounds on the left-hand side, or the traditional reactants. So we are literally looking at the reverse reaction. To make sure we have balanced chemical reactions, they're going to appear in the ratio that is shown in the balanced chemical reaction. Right? It's not explicit. I usually don't write ones like that. I just want to make sure it's different than the I. But it's not written, but it's implied that we have a 1 to 1 to 2 molar ratio. So for every 2 HI that react to go in the reverse direction, it produces 1 I2 and 1 H2. And we can increase that to a mole. Every 2 moles of HI that react in the reverse direction will produce 1 mole each of H2 and I2. However, I don't know if one molecule reacted, a mole reacted, or some random amount reacts, because it's going to reach an equilibrium concentration, and that doesn't necessarily need to be whole number amounts of like moles reacting. It needs to be whole number amounts of molecules. You can't have a half a molecule, but a mole has a trillion. You can definitely have fractions of a mole reacting. So the way we represent that is saying, okay, my reactants are being, my products are being consumed in a molar ratio of 2 to 1 to 1, and then I'm multiplying that by some amount that's going to tell me how much actually did react. So I'll just say X. I don't know how many reacted, but they react in a certain molar ratio. And then I can do the same thing for H2 and I2. So it's producing an amount of H2 and I2 in a molar ratio of 2 to 1 to 1. Equilibrium is going to be, I don't know why my zeros disappeared, but my equilibrium is just going to be adding the I and the C rows up. So 0 plus 1x is 1x. And then what we have for the HI is going to be a quarter molar minus 2x. So I haven't heard anyone talking in a while. I just want to make sure you guys can still hear me. Are we in good shape? Any questions? We all set? I can hear some noise. Because the only thing is, as soon as I start writing, I can't see if there's any interactions. That's the only problem. So I'd have to clear the screen. All right, so theoretically, we're done. Because it only asked me for equilibrium concentrations. Those are equilibrium concentrations, but it has an unknown variable in it, x, right? So what we're going to need to do is set up another equation so I can solve for x. Where am I going to get that from? It's actually going to come from k. And we already wrote this down earlier. We know that the k expression for this reaction looks like this. We also know it's equal to 57.0. So if I plug in my concentrations of HI, or my equilibrium concentrations of HI, I'd end up with an expression like that. So if I only pay attention to this part of what I wrote, it's actually a pretty straightforward math problem. So what I'm going to do is I'm going to clear the screen, rewrite what I have highlighted in blue, and then we'll keep moving on from there. So we had k equals, we said it was the 0.250 minus 2x squared. And then I'm just going to multiply both of those x's on the denominator together. And I'll replace that k with the number 57.0. So I look here, and I think this is probably, it's not frustrating. There's actually only a certain number of ways you can do this, but you're going to need to figure out what mathematical operations you need to do to solve for x. Effectively, this turns into an algebra problem. I spelled that wrong, but you know what I said. Algebra problem. So we're going to do it one way right now. There's going to be times when we need the quadratic equation. There's going to be other times we need to figure out how to solve for x. So unlike when we were trying to solve for the rate law of something based on experimental data, and I said there's only one way to do it, well, there's a lot of different ways to solve ice tables. So it's going to come down to algebra. What I see immediately, though, is that all of my x's, the things that I need to solve for, are associated with squares. What I could do, if I took the square root of the left-hand side of the reaction and the square root of the right-hand side, what I'll see is that if I take the square root of 57, I get the number 7.5498. It will be equal to, just get rid of the square that's around all of this mess, right? So I just get rid of that square effectively. And the same thing here, get rid of that square over the x. Now that problem is a lot more simple, right? Let me get rid of the parentheses so it makes it a little bit more straightforward. Actually, no, I'll leave them because I like them. It helps me visualize it. All right, I'm going to give you guys, let's say, a minute. I want you to do this math out because we still need to make sure we're practicing that math, because when the quizzes come, you want to make sure that you've been doing this all along. So give this a shot. Solve for x is what I'm asking for. And I've started the timer. You guys got about 55 more seconds to give it a shot. And I will cold call too, so make sure you're doing it. And this is weird. My AC in my house just kicked on. Apparently it must be getting pretty warm outside. Which is also terrible because I shouldn't be having the AC on in spring. All right, so we've had about a minute, so I want to open up the participant tab. So what I'm going to do is I'm going to have to erase this for a second, just so I can start using things on my computer again. All right, so let's do this. So if you don't have an answer, that's totally fine. Simran, do you have an answer for x? You were able to solve for a number?
Yeah, I got 0.026.
Yep, that's what I got, I believe. I'm trying to scramble through my notes. It is exactly what I got. I would add a little bit more sig fig on that, but I agree where we're going. I got 0.0262. And the only reason I'm attaching that third sig fig number is because the concentration was derived from amounts that had 3 sig fig. So I want to make sure I'm not losing anything. But I agree. And so anyone who didn't get that number, just double check your math, go a little bit more slowly through it. But this is where we should have ended up. We're still not done, though. Let me just wipe this for a second. I want to get this off my screen when it's recording. All right. So we have x equals 0.0262. Anytime we're doing an ICE problem, and this is going to go into chapter 16 and 17, you need to ask the question, what is x, right? Because we're not done. X is we're probably like, 80% the way there. We're almost done. But we need to know what x represents. So if we go back to our ICE table, and we look at our final row, which was our equilibrium row, right? We said it was x, and 0.250 minus 2x. What we see here is that x is equal to the concentration of H2 and I2, and then we could theoretically figure out the equilibrium concentration of HI, because x does appear in that equation, and it's the only unknown we need. So let's finish this off then. When you're reporting your answers, what I need to see is things organized, and I want all equilibrium concentrations next to each other, preferably stacked. It makes it much easier for me to grade than trying to find multiple things floating around on a page. So because things are online and I need to streamline things, this will be a requirement for full credit doing a problem. If I have to look for your answers in a nice table, I'm going to take points off. So I'm just asking for you guys to just organize your final answer. That's all I'm asking. So going through that, we realized that the equilibrium concentration of H2 was 0.0262. And we, Lauren, you were the one who answered. You were technically correct by just giving me a number. Because that was used solving the equilibrium constant, there's no unit. But a concentration is one of those things where you almost have to like figure out what you were doing and make sure, I started with molar, so my final answers will be in molar, even though I did most of my math without units. The concentration of I2 at equilibrium is equal to the same amount. It's not coincidence. They're just formed in 1-to-1 molar ratios, so that's why they're the same amount. And then our equilibrium concentration of HI, we said was the expression, or the equation 0.250 minus, make that a bracket, 0.0262 times 2. If you do that math out, what we should be getting is the equilibrium concentration for HI as well. So the nice thing about equilibrium tables is you can always double check your work. We already know the expression is going to be the equilibrium concentration of HI squared over the concentration of hydrogen to the first multiplied by the concentration of I2 to the first. This was the second problem we did at the start of lecture, and we already calculated it. The exact number we got was 57.1. I'm going to say within rounding error, which because actually it is due to rounding error. They're the same. So we started with 57, we end with 57. We know we did it right. All right. So we're exactly ending at the same time my last class did. So I'm going to stop lecture here for today because these problems get too long that we can't finish them in 10 minutes. So I don't want to start and stop. So we'll stop here a little bit early. It's a gorgeous day outside. I know people have been cooped up for 2 weeks. Make sure you get outside, even just a little bit. Obviously, keeping distance between yourself and be smart. But put it this way. I was going to give additional videos to watch over the weekend. I realized we have plenty of time in the syllabus. We'll do more ice tables on Monday. So there should be nothing for you to watch over the weekend. So make sure you get out, stay healthy, and enjoy some good weather. So I'm going to let you guys go now. You're welcome to sign off at any point. I'm going to stick around a little bit longer if there's any particular questions we want to address. And if not, feel free to head out. Oh, I can see stuff in the chat now that I've stopped using the stylus. Let's see if I can pull that up. Oh, it's great.
I actually have a small question.
Yeah.
Just about the rearranging of the 7.5498 equals 0.250 minus 2x over x.
Mm-hmm.
I had my brain froze and I don't really remember how I was supposed to rearrange that.
All right, so again, say it a little bit slower. I just got to find it in my notes where you were talking about. Say again.
The 7.548.
Mm-hmm. Yeah.
Am I just multiplying by x and then adding 2x,
Yes.
solving that way?
Yep, that's exactly how you do it.
Okay.
So, how about this, Hannah? Yeah. So yeah, you did it right then. So why don't you give that a shot? If for some reason it still gives you a problem, let me know, and then what we can do is we'll just make an office hour sometime, and then just make sure that you know how to do it.
Okay, cool. Thank you.
Yeah, no problem.